Let's work a Thevenin equivalent problem, and in particular here's the circuit that I want to look at. We have a dependent source, connected to a couple of resistors, then an independent voltage source of 12 volts. That's followed by a resistor, and then we have a couple of more resistors. And in order to make sense, I need to define what dependent variable we're using. We're using I sub x. I sub x, let's say, is the current flowing through the 2K ohm resistor. And let's find then the Thevenin equivalent in this above circuit between nodes A and B, where here is B and here is A, and I want the Thevenin equivalent looking into the left of those terminals or nodes. And this particular circuit has a dependent source, an independent source, and we can solve then this problem a couple of different ways. We could zero the independent source if we didn't have that dependent source, but since we have the dependent source, we need to keep that independent source in there to give us something to work with to energize that dependent source. And the solution that we are going to use then is we are going to find the result from two different circuits. One, we're going to open up the terminal or the circuit at nodes A and B and find the open circuit voltage across those two terminals. Then we will create a second circuit that shorts out the circuit between nodes A and B, and we'll determine the current flowing through that short-circuited path. With those particular circuits analyzed to find the open circuit voltage and the short circuit current, we'll use that to actually obtain our Thevenin equivalent, which we will describe as V Thevenin and Z Thevenin, where Z is our impedance. In this particular example, though, it should be clear that we're looking to find just a resistor for Z Thevenin, since there are no inductors or capacitors in our circuit. And our V Thevenin will be our open circuit voltage, and our Z Thevenin, which I just said would be a resistor, R Thevenin, is going to be the ratio of this open circuit voltage to this short circuit current. Let's then find the open circuit voltage. Again, we're going to have to analyze two different circuits, one with the terminals A and B opened, that's the V open circuit problem, and the other circuit, the second circuit, will be when those two terminals are short-circuited. To find V open circuit, let's open up nodes A and B. And here is now V open circuit. This was a 2K ohm resistor, this was 2K, this was 1K, and we have our I sub x flowing in the rightmost vertical branch. Let's go ahead and do mesh analysis, since we have two meshes and we have voltage sources. One is independent and one is dependent, but we don't have any current sources, and so it's looks like it might be a little easier if we just do a mesh analysis to try to find V open circuit. And V open circuit, I hope it's clear, will simply be this 2K times I sub 2 once we've found I sub 2. Let's now do our mesh analysis. With I1 and I2 that we've defined. Mesh 1 will say that we have, going from the lower left-hand corner, we enter the positive terminal of that dependent source, and that has a voltage transition plus to minus of 2000 I sub x. Then we have a voltage dropped across the 1K ohm resistor in the direction of I1. And then we have the voltage dropped across the 2K vertical, the first one in the middle, and that's 2K times I1 minus I sub 2, and we're back to where we started, and there's 0. We also can then write KVL around mesh 2. Starting again in the lower left corner, we'll have 2K times, now we want the drop to be positive going up, and so we now have I2 minus I1. That's the net current going up through that 2K ohm resistor. We'll have 2K times I2 minus I1 plus 12 volts plus 2K times I sub 2. So we now have mesh 2 is 2K I2 minus I1 plus the 12 volts plus 2K times I sub 2 is equal to 0. And we could now have two equations in two unknowns if we didn't have that dependent variable in our mix or in our equations. We have an I sub x. Hopefully it's clear though that in terms of the mesh currents that we have defined, I sub 2 and I sub x are the same. We can now use that fact in mesh equation number 1 to get rid of I sub x, and we'll end up now with our two equations in two unknowns that we were after. Or from mesh equation number 1, we now have 2000 I sub 2, or that's 2K I2 plus 1K I1 plus 2K I1 minus 2K I2 equaling 0. This is just 2K, and we have 2K I2 minus 2K I2, and this now leaves us with 3K times I1 is equal to 0, or I1 is equal to 0 in this circuit that we're analyzing to find the open circuit voltage. If we now look at what equation 2 gave us, again we were trying to find I2 because we need I2 to find V open circuit. From equation I2, or I'm sorry, from equation that results from mesh 2, and if we now use I1 is equal to 0, let's just wait just a minute before we do that, but we now have 2K I2 minus 2K I1 plus 12 plus 2K I2 is equal to 0. Now from here we know that I1 is equal to 0, and we have then that 4K times I2 is equal to minus 12. I2 then becomes minus 12 over 4K, or minus 3 divided by 1,000, or minus 3 milliamps. That's I2. And what we were looking for was our open circuit voltage. And we started off knowing what that was. That was simply the 2K times I sub 2. We now know what that I sub 2 is. The K and the 10 to the minus 3 cancel, and we're left then with our open circuit voltage being not minus 6 volts. That was half of our analysis that we need to perform. We now need to find our short circuit current. To do this, we need to sketch or create the appropriate circuit, which is different from the circuit that we just had, in that we now short the terminals between terminal A and terminal B. Here's 1K. Here's our 2K. Again, this is 2000 I sub X as a dependent voltage source. Here is our source of 12 volts. Here is our 2K resistor. There's terminal A and terminal B, or node A and B. And now, to do this analysis, we need to short those, and we are now wanting to find I short circuit. And we also know that this is I sub X. In this particular circuit, hopefully you can now see that some things are going to cancel or be removed. If you look at this, hopefully it's clear that if I had a current going in here, or that same current coming out there, since you could think of this as just being a big node, that's the same current. But now, with respect to that current going in, how much of that current is going to want to go here, and how much is going to want to go to the right? Well, hopefully it's clear that since the current going to the right is to a zero resistance wire, and the current going down has some resistance associated with it, all of that current coming in up above is going to go as I short circuit, and consequently the current going down that vertical branch, which we've defined, or which is defined as I sub X, that's equal to 0. And that's the first observation I want you to make, which is I sub X is equal to 0. And that's because all of this current that was going into that branch or intersection of wires, all the current flows through the zero resistance wire, which is our I short circuit. If that's the case, then you can also, I hope, see that this forms a connection, and consequently this voltage source of 12 volts is dropped all across this 2K ohm resistor. And let me now label this as I sub 2, or maybe I should say I2. And what if I call this I1? Remember, we've just discovered that I sub X is equal to 0. And now, seeing that we're shorting out that 2K ohm resistor, all of that 12 volt source is dropped across the 2K resistor to give us I sub 2. And I'll call that the middle 2K resistor. that 12 volt source is dropped across the middle 2K resistor. Because of that, we can say that I sub 2 is just the 12 volt divided by 2K, or that's 6 divided by 1,000, or 6 milliamps. If we're doing that and realizing that I sub x is equal to 0, if this is now equal to 0, what we have dropped across the 1K is also the 12 volts. Or if you can't see that, you could say, well, I1 is just our 12 volts minus that dependent source voltage, which is minus 2000 I sub x all over 1K. But now we know in this analysis that I sub x is equal to 0. We now have 12 divided by 1K, or 12 milliamps. Now that we have I sub 1 and I sub 2, we've found I sub x, we can actually look down here and say, you know what, if we know all of those, then we can actually find I short circuit by a KCL at that bottom node. And all of these currents, I1 is coming in here, I2 is coming in, I sub x is coming in, and I short circuit is coming in. Hopefully then you can see that KCL at the bottom node allows us to say that I1 plus I2 plus I sub x plus I short circuit is equal to 0, or I short circuit is equal to minus I1 minus I2, since this is equal to 0, and we found I1 to be 12 milliamps, I2 is 6 milliamps, and we now have minus 18 milliamps for I short circuit. We've now analyzed the two separate circuits, one to find V open circuit, one to find I short circuit. We now can calculate what the Thevenin resistance needs to be, which is this ratio of the open circuit voltage to the short circuit current. The open circuit voltage was minus 6. The short circuit current was minus 18 milliamps. And now we have then the negative, or the minus signs cancel. We can take 6 and factor that into 18. We can take the 10 to the minus 3 upstairs, and we now have this is equal to 1/3 K ohm for our Thevenin, or 333 ohms. We now have the information that we need to model the Thevenin equivalent between nodes A and B. This is now 333 ohms, that's our Thevenin, and our V Thevenin is this minus 6 volts. Or if you don't like that V Thevenin being a minus 6 volts, we could just as easily rewrite that or redraw that and say, well, if I have a negative 6 with the positive and minus polarity that way, I could say that that's 6 volts for in the minus plus from top to bottom with my R Thevenin, which is 1/3 K ohm. And that's then the Thevenin equivalent for that original circuit that we looked at.